the video lecture on physics in petroleum engineering brought to you by Petroleum from Scratch. This is the final lecture in series application of pulley system in oil and gas industry. Up to now we have discussed about the pulley system in hoisting without considering the effect of friction. In today's video we will discuss what will happen if friction comes into the play. So first of all guys, due to losses caused by the friction, the efficiency of our hoisting system reduces. Now before proceeding further, we will discuss some important terms that will be helpful in our discussion. The first term is efficiency factor of block and tackle, also denoted by EF. It is nothing but the ratio of fast line load in absence of friction to the fast line load when friction is present. And guys, let me tell you one thing, that the magnitude of fast line increases due to presence of friction. We will see why this happens. So the value of EF is less than 1. The second term is sheave and line efficiency per sheave, denoted by K. It is a factor by which our tension reduces in the line when the line passes over the sheave, and this happens due to the friction. Okay, now let's discuss the expression for the efficiency factor and calculate fast line load and deadline load when a given hook load is provided. So let FL be our fast line load, and P1, P2, P1, P2, P3, P4 up to Pn are the tensions in the rope that are strung between the traveling block and the crown block. Starting from the fast line load FL, the tension in the fast line reduces to P1 when the line passes through this sheave. This is happening due to friction, and the value of P1 is given by FL into K, where K is the sheave and line efficiency per sheave. Okay. Now similarly, when this P1 line crosses this sheave, the tension further reduces to the P2, whose value is given by P1 into K or FL into K square. In similar way, the tension goes on reducing due to friction. The value of tension in nth line is given by P1 into K ki power n. Okay, here comes an important point guys. The value of tension in dead line is also Pn, the same value in this line, same value of tension in this line, cause the sheave you are seeing here is a stationary sheave, so no friction comes into the play and value of tension is not reduced further. So these end lines are supporting this hook load W. So we will write a equation here. W is equal to P1 plus P2 plus P3 up to Pn, and writing them in the terms of fast line load and K, we will come to this equation. So this is nothing but a geometric series we have studied in our school time, whose sum is given by this formula, Sn equal to A into R to the power n minus 1 divided by R minus 1, where A is the first term, which in our case is K, and R is the ratio between the first term and second term, which is also K. So this expression will reduce to this expression, and writing here it will become this. So from this we can calculate the fast line load. And remember guys, this is the value of fast line load in the presence of friction, and in absence of friction we have already discussed what will be the value of our fast line, as the hook load is uniformly distributed in the line in case of absence of friction. So fast line load will be given by W by N directly, and let us denote our this fast line load in absence of friction by PAV. Okay, so now so now from the definition of efficiency factor, that is the ratio of the fast line load in absence of friction to the ratio of the fast line load in the presence of friction, we can calculate the EF, and its value is given by this expression. And also we have discussed about the deadline load. Filling line by the draw work. For doing this work, power is supplied to the draw work. And the power requirement is given by the basic equation we have studied in our childhood, that is force into the velocity. And in this case the force is fast line load and velocity is fast line velocity. And as we have discussed earlier, the fast line velocity is nothing but n times the velocity of traveling block. And fast line load we have derived in our previous slide, that is hook load divided by n divided by efficiency factor. Putting these two values together, we come to our final equation, that is power is equal to hook load into velocity of traveling block in divided by efficiency factor. And guys, this is in SI units, so converting it into field units, a constant of 33,000 will come in the denominator. And in field unit we are taking hook load in lbf, pound force, and velocity in feet per minute. We will discuss unit conversion in one separate video lecture completely. Now this is the power required, and power supplied will be somewhat greater than the power required, as some part of the power will get lost due to the friction or some other factors due to mechanical efficiency of parts of draw work. So power input can be calculated by dividing this power required by a mechanical efficiency, and that mechanical efficiency is a number between 0 to 1. So obviously power input is greater than power required. So that's it guys. Okay guys, that's all for pulley system. Hope you guys like it. We will start Bernoulli's theorem and its importance in our oil and gas industry from the next lecture. Until next time, thank you.